At the Computer Graphics and Animation Group, we're continuing our work toward a knowledge-based animation environment which includes robotics and AI technologies integrated with modeling and rendering tools. The connection machine is a parallel processor with a large number of interconnected, small-scale CPUs. Here, a ray tracing algorithm is run on a connection machine with 16,000 processors, in which we assign one ray per processor. This sequence was computed at about 40 seconds per frame. RenderMatic is a modular, extensible library of graphics routines written in C that makes up our graphics software testbed. Our latest extension is a device-independent implementation of the A buffer, which provides anti-aliasing, transparency, and digital matting. Lemon is a stylized character who lives in a microworld, here displayed on a Trillium image generator. We are developing a prototype representation of human motor behavior that will allow Lemon to interact autonomously to the questions and commands of a child in a real-time dialogue. We use forward kinematics to program the grasping motion of a human-like hand. Next, we add collision detection. Now the hand can be directed to grasp convex polyhedra of any reasonable size or shape. Inverse kinematics allows us to compute joint angle changes needed to move the arm and hand to a particular location in space. Here are two 7-degree of freedom arms. The only input to the inverse kinematics algorithm is the path of the ball. The arm movement is computed automatically. This is a very general technique. In this scene, you'll see creatures modeled as 9-link kinematic chains with a polygonal skin stretched over them, moving down a flight of stairs. Each creature computes a path down the steps, which may vary in rise and run. Inverse kinematics is used to guide the motion along this path. Here, the same inverse kinematics code is used to control the leg motions of quadruped creatures moving automatically across a varying ground surface. We intend to improve the realism of these gaits by adding dynamic simulation to compute correct swinging motions of the legs and the pitching and rolling of the body as it moves over the landscape. In a complementary approach to gait generation, rhythm generators control the stepping and swinging of the legs of this hexapod. Reflex action checks for firm support, so that one leg doesn't lift until the neighboring leg has touched down and taken up the load. By varying the frequency and phase relations of the stepping oscillators, smooth gait changes can be achieved. This kind of gait control is preferred when the terrain is not too uneven or cluttered. All objects, not just simulated organisms, have appropriate behaviors. If an animated figure drops a glass, for example, it should fall and shatter, and even generate the sound of breaking glass. These polyhedra appear to fall in a simulated gravity field. We don't compute friction or inter-object collisions, but the proper linear and angular velocities are approximated.